Derivatives of polynomials and exponential functions. We start with the derivative of a constant function. Remember, a constant function is a horizontal line. Therefore, the slope of any line tangent to it will be 0. So the derivative of the constant function is 0. We can also prove this using the definition of the derivative, but it's really unnecessary since this is a really obvious observation. Secondly, the derivative of x is 1. So think of the function y equals x. The slope of this line is always 1. And if we pick a point on the curve, the tangent line to it will be this line itself. And so the slope of any tangent line is also 1. Again, we could prove this using the definition of the derivative, but again, this is a pretty obvious observation. The power rule. If n is any real number, then the derivative with respect to x of x to the n is n times x to the n minus 1. We won't be proving this rule, but I would encourage you to pause the video and do a couple of examples using the definition of a derivative to see that it's true. For example, you could take the function f of x is equal to x cubed, and you can demonstrate using the definition of the derivative that the derivative is 3 times x to the second power. So notice that the derivative is, you take the power down in front, so we have the 3 here, and then you keep x, but you subtract 1 from this power, which is how we get the 2 there. This rule is a quantum leap of sorts, because now when we want to take a derivative of x to any real number power, we don't have to use the definition any longer. We can simply use this rule. Let's go through a few examples. So here in the first example, we have the function f of x is equal to x to the 6th power, and we want to find the derivative f prime of x. So the rule says we take the power 6, we bring it down in front, and then we subtract 1 from that power. And when you do the math on this, you get 6x to the 5th power. And it works no matter how big the power is. So in the second part of this example, if y equals x to the 1000th power, then y prime is 1000 times x to the 1000 minus 1. And of course, 1000 minus 1 is 999. So the derivative would be 1000 x to the 999 power. And although we won't be using functions like this to do actual examples, this example serves to show you that the rule is true no matter what the power is. In the third part of this example, we have y equals t to the 4th power. So first I want you to notice that when we talk about the derivative, it's dy dt, because the independent variable is t. So we are taking the derivative with respect to that variable. But it works the same way. So the derivative is going to be 4 times t to the 4 minus 1, which ends up being 4t to the 3rd power. And finally, we have d dr of r cubed. So again, we have a function r to the 3rd power. We are taking the derivative of that function with respect to the variable r. And so the derivative here, of course, will be 3r to the 2nd power. In the second example, we have a couple of slightly more complicated problems. So you have to be very careful not to use the power rule when the variable is in the denominator of a fraction. So when you have a function like 1 over x squared, first we need to rewrite this as x to the negative 2 power. And now when I find the derivative, I'll write f prime of x is equal to, And we do the same process. So the power negative 2 is going to come down in front of the variable there. So we get negative 2x. And then the power negative 2, we subtract 1 from it. And so the resulting derivative is negative 2x to the negative 3. And then we're going to rewrite this by remembering that x to the negative 3 is the same as 1 over x to the positive 3. And so we have negative 2 times 1 over x to the 3. And then multiplying these together, we get negative 2 over x cubed. So it's very important when you use the power rule for derivatives that your variable is not in the denominator of a fraction. If it is, you need to move it up to the numerator by using a negative exponent, and then you can apply the power rule. Same thing is true here. Y equals the cube root of x squared. I can't apply the power rule to x squared because we have a cube root around it. So we need to remember that this is really x squared quantity to the 1/3 power. This is the definition of a cube root. And then we can multiply those exponents together. 2 times 1/3 is 2/3. So after rewriting the function to be y equals x to the 2/3 power, now I can find the derivative, which I'll call y prime, and it will be 2/3 x to the 2/3 minus 1. And this is 2/3 x to the negative 1/3. And then just like in the previous example, I'm going to rewrite x to the negative 1/3 as 1 divided by x to the positive 1/3. And then multiplying these fractions straight across, we end up getting the derivative is 2 divided by 3x to the 1/3. And you can leave your answer like this, but you can also rewrite this answer to be 2 over 3 times the cube root of x. I'll be honest with you though, I think this answer is probably better. When you try to rewrite it back into radical form, sometimes this can cause trouble. In the next example, we'll demonstrate that you can find the equation of a tangent line to a curve by using this new rule. So in this case, we want to find the equations of the tangent line and the normal line to the curve y equals x radical x. And just for clarity, the function x radical x is this curve right here. Now the tangent line is going to be very familiar to you. That's this line right here. The normal line is just the line that is perpendicular to the tangent line. So what makes the green line here, the normal line, is that there's a 90-degree angle between the normal line and the tangent line. So we'll talk about how to find the normal line in just a second, but it turns out that it's not that big of a deal, as long as you know what it is. So first of all, let's find the tangent line. And so we have the curve y equals x times the square root of x. Let's remember that this is x to the 1 times x to the 1/2. And using rules of exponents, we can add these together to get x to the 3/2 power. So that's our function. The derivative of our function, which we need in order to find the equation of a tangent line, is going to be 3/2 x to the 3/2 minus 1, which is 3/2 x to the 1/2. Or if you like, you can say it's 3/2 times the square root of x, which is also the same as 3 square root of x divided by 2. Now, just a quick point, all three of these are acceptable forms of the derivative, but this last one is perhaps the most useful when it comes to actually computing the slope of a tangent line. So let's remember that the slope of the tangent line, which we'll call m, is nothing more than the derivative dy dx evaluated when x is equal to the x-coordinate of the point of tangency, which in this case is x equals 1, right? Because that's the point that they gave us up here. So our derivative is 3 square root of x divided by 2, and we're going to evaluate that when x equals 1. And this is going to be 3 times the square root of 1 divided by 2, and the square root of 1 is 1, so we get 3 halves. That's the slope of the tangent line. Now let's just mention over here the slope of the normal line is, and I'm going to call it m with a little perpendicular symbol, it's going to be negative 2/3. And to know this, you just simply need to remember that if you know the slope of a tangent line, the line perpendicular to it has a slope which is the opposite reciprocal of the other slope. So the opposite reciprocal of 3 over 2 is negative 2 over 3. Now both of these lines intersect the curve at the point 1, 1. And so now to find the tangent line, or to find the normal line, all I have to do is use the respective slopes and plug it into the equation of a line formula at the point 1, 1. So for the tangent line, we get y minus 1 equals 3 halves times x minus 1. And for the normal line, we get y minus 1 is equal to negative 2/3 times x minus 1. And if I just multiply this out, I'm going to get 3 halves x minus 3 halves. And then when I add 1 to both sides, I end up getting y equals 3 halves x minus 1/2. So this is the equation of the tangent line. And for the normal line, I get negative 2/3 times x, and then plus 2/3 when I multiply negative 2/3 times negative 1. And then adding 1 to both sides, I get y equals negative 2/3 x plus 5/3. Next, we have a couple of very useful rules. The first rule states that if you take a derivative of a constant multiple of a function, that is going to equal the constant multiple multiplied by the derivative of the function. So for example, if f of x is 5x squared, and I want the derivative of this, to get f prime, I don't have to worry about taking the derivative of 5. It's simply going to be 5 times the derivative of x squared. And so that just becomes 5 times 2x, right? Because the derivative of x squared is 2x to the 1. And then when I multiply this out, I get 10x. So when you have a constant multiple of a variable to a power, you can take the derivative of the variable to the power and then just simply remember to multiply by the constant multiple that was there. A couple of other rules. The sum and difference rules simply states that the derivative of the sum of two functions is the sum of the independent derivatives. And likewise, the derivative of the difference between two functions is the difference between their derivatives. So for example, if g of x is equal to x cubed minus x squared, and I want the derivative g prime of x, what we're doing here is we're taking the derivative of x cubed minus x squared. But to do that derivative, I'll just focus on taking the derivative of x cubed and then minus taking the derivative of x squared. So the derivative of x cubed we know is 3x squared, and the derivative of x squared is 2x. So it allows you to focus on one thing at a time. So these are two rules that are extremely useful. In our next example, we want to find the points on the curve y equals x to the fourth minus 6x squared plus 4, where the tangent line is horizontal. So let's remember that a horizontal line has a slope that is 0. So when you're looking for a horizontal tangent line, we need to find the x values where the derivative, in this case we'll say dy dx, is equal to 0. So first, let's compute dy dx. The function y is x to the fourth minus 6x squared plus 4. So the derivative dy dx is going to be the derivative of x to the fourth minus 6 times the derivative of x squared plus the derivative of 4. Now, you don't have to show this work when you're doing examples, but I wanted to point out that these are just the properties that we learned on the previous page. So the derivative of x to the fourth is 4x to the third, and then we have minus 6 times the derivative of x squared, which is 2x, and then plus the derivative of 4, which is 0. And so our derivative is 4x cubed minus 12x. Now to find the points where the tangent line is horizontal, we need to take this derivative and set it equal to 0. Since the derivative represents the slope of the tangent line, solving this equation for x will tell us where the horizontal line, where the tangent line is horizontal. So to solve this equation, first I'm just going to factor out a 4x, and when I do that I get x squared minus 3 left over, and then I'll take 4x and set it equal to 0. Dividing by 4 gives us x equals 0, and then the other factor, x squared minus 3, set it equal to 0, and we get x squared is equal to 3. And to solve this, I take a square root of both sides, and I get x is equal to plus or minus the square root of 3. Now, these are the x coordinates where you have a horizontal tangent. But in the example, they say find the points on the curve where the tangent line is horizontal. So we have the x values. We need to find the corresponding y values. So for this, we're going to take each of our solutions over here, starting with x equals 0, and we're going to find the y coordinate when x equals 0 by plugging it into the original function. So when x equals 0, we get y equals 0 to the fourth minus 6 times 0 squared plus 4, and this is y equals 4. So the first point on the curve where we have a horizontal tangent is the point 0, 4. If x is equal to the square root of 3, y is going to be the square root of 3 to the fourth power minus 6 times the square root of 3 squared plus 4. Now, the square root of 3 to the fourth power is actually 9. And then we have minus 6 times the square root of 3 squared is 3, and then plus 4. And then doing the math, 9 take away 18 is negative 9, plus 4 is negative 5. So radical 3, negative 5 is another point on the curve where the tangent line is horizontal. And finally, we have x is equal to negative radical 3. Y is going to be negative radical 3 to the fourth power minus 6 times negative radical 3 squared plus 4. And this actually yields the same result, negative 5. So we have negative radical 3, negative 5 is the third point on the curve where we have a horizontal tangent. And let's take a look at the graph just for confirmation. So here you can see the function, and we have 3 places where we have a horizontal tangent. 0, 4, negative radical 3, negative 5, and positive radical 3, negative 5. Next, we have an example of motion. The equation of motion of a particle is given here, where s is measured in centimeters and t is measured in seconds. Find the acceleration as a function of time. And then also, what is the acceleration after 2 seconds? So let's remind ourselves that if we have a position function s, in this case equal to 2t cubed minus 5t squared plus 3t plus 4, the first derivative ds dt gives us the velocity. And in this case, the derivative here is going to be 2 times 3t squared minus 5 times 2t plus 3 times 1, and the derivative of a constant, of course, is 0. And so our velocity function, which is the first derivative, is 6t squared minus 10t plus 3. But they ask about the acceleration. So then we need to remember that the acceleration function is the derivative of the velocity function. And the derivative of the velocity function is the second derivative of the position function. So to get the acceleration function, we just need to take the derivative of this velocity function, which is 6 times 2t minus 10 times 1 plus 0. So again, all I'm doing here is just using the power rule, right? So the derivative of t squared is 2t to the 1, and then we have to remember to multiply that by 6. And likewise here, the derivative of t is just 1, so we have negative 10 times 1, and the derivative of a constant is 0. And so our acceleration function is 12t take away 10. So that's one part of our answer. And now we want to know, what is the acceleration after 2 seconds? So after 2 seconds, the acceleration is going to be 12 times 2 take away 10, which is 24 minus 10, which is 14. And this will be centimeters per second squared. Now let's focus our attention on exponential functions. So an exponential function is a function f of x equals b to the power x, where b is a positive number that is not equal to 1. We want to talk about what is the derivative of this function. So for this, we have to go back to the definition of a derivative. We're going to take the limit as h goes to 0, f of x plus h minus f of x divided by h. Now, f of x plus h is what you get when you plug x plus h in for x into your function. And so this will be b to the power x plus h. So applying this definition of a derivative, we get the limit h goes to 0 of b to the x plus h minus f of x, which of course is just b to the x, divided by h. Now, if you just plug in h equals 0, you will get 0 divided by 0. So we have to simplify this expression. And this is where it gets a little bit tricky. We're going to remember that there is a property of exponents that would allow us to write b to the x plus h as b to the x times b to the h. This is the property that says if you have a common base and you're multiplying together, you can keep that base and just add the exponents. And so what I'm doing is taking that property, but I'm using it to take this apart. So I'm going to rewrite b to the x plus h here in this way. So this becomes the limit as h goes to 0, b to the x times b to the h minus b to the x divided by h. Now from here, what we can do is we can actually factor out the common factor, which is this b to the x here. So we get b to the x times b to the h minus 1 divided by h. And if I now take out the b to the x, because b to the x does not have an h in it, so we can factor it out of the limit completely, we get b to the x times the limit as h goes to 0 of b to the h minus 1 divided by h. So if I just summarize what we have, if we start with the function f of x equals b to the x, we now know the derivative of that function is b to the x times this limit. And the question is, what does this limit equal? Well, it turns out that this limit is always a number, and the number is dependent on the value of b. But there is one very special number for which this limit is equal to 1. So I'm going to write down if b is equal to the number e, which, if you recall, e is a number 2.71828, etc. If b is that number, then the limit as h goes to 0 of e to the h minus 1 divided by h is equal to 1. So if b is the number e, this limit is 1. And in that case, we can write f of x would equal e to the x, and f prime of x would also equal e to the x, because the derivative is e to the x times this limit. But again, this limit is 1 if b is the number e. And for right now, we're just going to focus on this special case. So what we have is perhaps the most important derivative in all of mathematics, and that is the derivative of the function e to the x is equal to itself. So as a quick example of this last result, let's find an equation of a tangent line to the curve at the given point. And so the curve we have is y equals 2e to the x plus x, and the point of tangency is the point 0, 2. So again, to find the equation of a tangent line, we need the derivative. So dy dx is equal to, let's focus on the derivative here. The derivative of 2e to the x is 2 times the derivative of e to the x, which of course we know is e to the x. Plus, and then the derivative of x is 1. And so the derivative of this function is 2e to the x plus 1. So now the slope of your tangent line is going to be this derivative evaluated when x is equal to 0, because we know that x is this value right here. And that is going to be 2e to the 0 plus 1. Now remember, e to the 0 is 1, so we have 2 times 1 plus 1, which is 3. So the slope of our tangent line is 3. The point of tangency is the point 0, 2. And now I can find the equation of the tangent line. Oops, got to plug it in correctly. Y take away 2 is equal to 3 times x minus 0. And if you solve for y here, you end up getting y equals 3x plus 2. So equations of tangent lines are always the same. All we're doing now is applying that concept to more functions, because we now know how to take derivatives of more functions. And that concludes this lesson.